So let us discuss the remaining questions of conicoids, and in that specifically ellipsoid. So there are only 3-4 questions left, and let's discuss them today to wrap this topic. So the question number 1 says that there are 3 points P, Q and R which are taken on this ellipsoid. So there are 3 points. Let's say my P point is x1, y1, z1, and my Q point is x2, y2, z2, and my R point is x3, y3, z3. So the question says that these 3 points lie on the given ellipsoid, that is basically x square by a square plus y square by b square plus z square by c square is equals to 1. Also let me assume that, also the question says that these 3 points P, Q are on the ellipsoid such that the line joining OP, OQ and OR are mutually perpendicular. So the question says that line joining origin to point P, that is OP, likewise OQ and OR are mutually perpendicular. So let me assume that L1, M1, N1 are direction cosines of line OP. Likewise L2, M2, N2 be direction cosines of line OQ, and L3, M3, N3 be direction cosines of line OR. Also let's assume that these line OP, OQ and OR are a distance R1, R2, R3 away from origin. So if that is the case, I can find out equation of line OP. So my equation of a line OP will be basically x minus 0, because line OP is passing via origin and it has direction cosine as x1, is equals to y minus 0 upon m1 equals to z minus 0 upon n1. And since I have assumed that it is distance r1 away from origin, so I can equate it with r1 to get the point P. So basically my coordinates of point P, that is x1, y1, z1, will be basically equals to L1 R1, M1 R1, N1 R1. So this is basically my point P. Likewise I can find out the coordinates of point Q and R. So my point Q will be is equal to L2 R2, M2 R2, N2 R2, and my point R will be basically equals to L3 R3, M3 R3, N3 R3. So in the question it says that these 3 points are lying on the ellipsoid. So if these are lying on the ellipsoid, then the points must be satisfying the equation of ellipsoid. So if that's the case, let's just substitute value of point P, Q and R in the given ellipsoid. So using that, we'll get L1 R1 square by A square plus M1 R1 square by B square equals to N1 R1 square by C square equals to 1. I got this when I substituted point P in the given ellipsoid. So from here I'll get L1 square by A square plus M1 square by B square plus N1 square by C square is equals to 1 by R1 square. So let us name this as 1. So likewise if I substitute Q in the ellipsoid, I'll get L2 square by A square plus M2 square by B square plus N2 square by C square is equals to 1 by R2 square. Let's name it as 2, and when I'll substitute R in ellipsoid, I'll get L3 square by A square plus M3 square by B square plus N3 square by C square equals to 1 by R3 square. So let us name it as 3. So if you observe that the question says that these line OP, OQ and OR are mutually perpendicular. So if these are mutually perpendicular, then they must be satisfying, their direction cosine must be satisfying certain conditions, that is L1 square plus L2 square plus L3 square equals to 1. Likewise summation mi square, where I varying from 1 to 3, is also equals to 1. and summation ni square, where I is varying from 1 to 3, is also equals to 1, and summation li mi equals to 1, summation li ni equals to 0, and summation mi ni is equals to 0. And from here, in all these three, I is varying from 1 to 3. So these are the conditions which I got using a mutually perpendicular relation of line OP, OQ and OR. So if I add 1, 2 and 3, I'll get basically 1 by A square into L1 square by L2 square plus L3 square plus 1 by B square into M1 square plus M2 square plus M3 square plus 1 by C square into N1 square plus N2 square plus N3 square is equals to 1 by R1 square plus 1 by R2 square plus 1 by R3 square. So, and using mutually perpendicularity condition, this term is basically equals to 1. Likewise, this is equals to 1 and this is also equals to 1. So, from here I get 1 by A square plus 1 by B square plus 1 by C square equals to 1 by R1 square plus 1 by R2 square plus 1 by R3 square. So, let us name this relation as 4. So the question further says that the plane, we are supposed to prove that the plane PQR touches a fixed sphere. So till now we have got that this is x-axis, this is y-axis and this is z-axis. So if this is, let's say, my point P, this is my point Q, and let's say this is my point R. So if I join OP, likewise I can join OQ and OR. So OP is basically my R1, OQ is my R2 and OR is my R3. So if I just rotate this coordinate system XYZ and get a new coordinate system, let's say X dash, Y dash and Z dash. So in that system, the plane PQR is making intercept R1 with X dash, R2 with Y dash and R3 with Z dash. So in new system, X dash, Y dash, Z dash, plane PQR has intercept as R1, R2 and R3. So if that's the case, then using the general equation of plane which makes intercept with x, y and z axis, I'll get the plane PQR in x dash, y dash and z dash axis as x dash by R1 plus y dash by R2 plus z dash by R3 is equals to 1. Also I can do so because my OP, OQ and OR are mutually perpendicular to each other. So that's why I am able to rotate this XY plane to get new coordinate system X dash, Y dash, Z dash, which has same origin as the system X, Y and Z. If these are not mutually perpendicular, then I cannot say that these R1, R2, R3 will basically act as intercept. So I got this as equation of plane PQ. Now if I find out a distance of plane PQR from origin, that will be basically 0 plus 0 plus 0 minus 1 divided by R1 raised minus 2 plus R2 raised minus 2 plus R3 raised minus 2. So this is basically distance of plane PQR from origin, that is 1 upon 1 by R1 square plus 1 by R2 square plus 1 by R3 square. So this is distance of this is distance of plane PQR from origin. Also this distance will be constant even if I take plane coordinate system xyz, because distance is anywhere a scalar quantity and it does not depends on the coordinate system which we are choosing. So distance of plane PQR will be equals to 1 by r1 raised minus 2 plus r2 raised minus 2 plus r3 raised minus 2 from origin is equals to this from origin in both xyz and x dash yz z dash plane. Now if I consider equation sphere that has center basically 0 comma 0 comma 0, and if I take this as basically radius of the sphere, so I'll get my sphere as x square plus y square plus z square, as here there will be under root. So I'll get my equation of sphere as 1 by r1 raised minus 2 plus r2 raised minus 2 plus r3 raised minus 2. So this will be basically my equation of sphere which has center as origin and this as radius. And since this is the radius of sphere and this plane will basically act as tangent plane to the sphere, because the radius and the distance between origin and the plane is same and origin acting as center to this sphere. So basically this plane is tangent plane to this sphere. And since we have calculated from 4 that this 1 by r1 square plus 1 by r2 square plus 1 by r3 square is equals to 1 by a square plus 1 by b square plus 1 by c square, I can use this relation here in an equation of sphere. So if I do so, I'll get x square plus y square plus z square is equals to 1 upon 1 by a square plus 1 by b square plus 1 by c square. So from here I got my radius of sphere as constant, because they have already provided us equation of ellipsoid, that is x square by y square plus x square by a square plus y square by b square plus z square by c square equals to 1. So this is basically a fixed equation of ellipsoid. So a, b, c and a, b, c will act as constant for this particular situation. So I got my radius of sphere as fixed. So from here I can say that the plane PQR touches a fixed sphere, because I have already chosen center as origin and this distance is basically will always be constant for given values of a, b and c. So plane PQR touches a fixed sphere, and that's what we are supposed to prove in this question, I guess. Yeah. Also you can do this question by assuming like origin as vertex, and you can basically find out equation of cone, and then you can use the coefficient thing, that coefficient of x square plus y square plus z square will be equals to 0 for 3 mutually perpendicular generators. Like that also you can approach this question. So let's move on to next question. So the next question says that find the tangent plane to this ellipsoid which are parallel to the given plane. So they have given us a equation of plane, that is Lx plus my plus nz equals to 0. So any equation of plane that will be parallel to this plane will be of form Lx plus my plus nz is equals to p, let's say. So the question says that this plane P is basically acting as tangent to given ellipsoid. So the given ellipsoid is x square by a square plus y square by b square plus z square by c square is equals to 1. So if 1 is tangent to 2, 1 is tangent to 2, then using tangency condition I'll get L square upon 1 by a square plus m square upon 1 by b square plus n square upon 1 by c square is equals to p square. So if I simplify it, I'll get a square L square plus m square b square plus n square c square is equals to p square. So from here I'll get my P as plus minus under root a square L square plus m square b square plus n square c square. So the required equation of plane, which is basically parallel to this and tangent to this, is Lx plus my plus nz is equals to plus minus under root a square L square plus m square b square plus n square c square. So these are basically equations of plane that are acting as tangent to the given ellipsoid. So let us move on to next question. So the question says that prove that locus of pole of the tangent plane to this conicoid with respect to this conicoid is this. So they have given us two conicoids. Let us name them as C1 as ax square plus by square plus cz square is equals to 1, and the conicoid second is alpha x square plus beta y square plus gamma z square is equals to 1. So the question says that locus of pole of the tangent plane to this conicoid. So let us assume that let Lx plus my plus nz is equals to p be tangent to conicoid C1. So if that is the case, then using tangency condition I'll get L square by a plus m square by b plus n square by c is equals to p square. So let us name this equation as star. Now let a dash, b dash and c dash be pole to the plane which we have assumed. Let's name that as 1. Be pole to plane 1, and that pole is with respect to the conicoid alpha x square plus beta y square plus gamma z square equals to 1. And if you know the definition of pole, then pole of a given plane is basically any such point at which polar plane is basically equals to given plane. So polar plane of this coordinate with respect to this point will give us the same plane as this. So let us find out polar plane with respect to the given plane. So polar plane with respect to conicoid C2 at point a dash, b dash, c dash would be basically a dash alpha x plus b dash beta y plus c dash gamma z is equals to 1. So let us name this equation as star dash. Now using the definition of pole of a plane, this star dash and star plane must be representing this star dash and this, the plane which we have assumed, which is acting as basically tangent to C1, must be representing the same plane. And if that's the case, then the direction cosine of their normals must be proportional to each other. So using that relation, I'll basically get a dash alpha by L must be equals to b dash beta by m, and that must be equals to c dash gamma by n, and which will be basically equals to 1 by p. So from here I can basically get values of Lm and n. That will be L will be basically p a dash alpha, m will be p b dash beta, and my n will be basically p c dash gamma. Now I can just use these L, m and n in this star equation to basically get the locus of pole, that is a dash, b dash and c dash. So if I do so, I'll get p a dash alpha square by a plus p b dash beta square by b plus p c dash gamma square by c is equals to p square. So if I simplify it, I'll get a dash square alpha square by a plus b dash square beta square by b plus c dash square gamma square by c is equals to 1. So a locus of a pole a dash, b dash, c dash would be basically x square alpha square by a, y square beta square by b plus z square gamma square by c is equals to 1. So this is basically the required equation, locus of pole. So this is, I guess, what we are supposed to prove in the question. So let us move on to next question. So the next question says that derive the equation of plane which touches this surface and parallel to this plane. So they have given us a equation of plane, that is 4x plus 20y minus 21z is equals to 0, and equation of given ellipsoid is 4x square minus 5y square plus 7z square plus 13 equals to 0. So if I simplify this equation of ellipsoid in general form, I'll get minus 4 by 13 x square plus 5 by 13 y square plus minus 7 by 13 z square is equals to 1. So the question says that any plane parallel to this given plane is acting as tangent to the ellipsoid. So equation of plane parallel to P will be basically 4x plus 20y minus 21z is equals to P, let's say. So this plane is acting as tangent to this ellipsoid. So using tangency condition, I'll basically get 4 square upon minus 4 by 13 plus 20 square upon 5 by 13 plus minus 21 square upon minus 7 by 13 is equals to P square. So if I simplify it, I'll get minus 4, 13 into minus 4 plus 20 into 4 minus 21 into 3 is equals to P square. So from here I got my P square is equals to 13 into minus 4 plus 80 minus 63, which is basically equals to 13 into 13. So from here I got my P as plus minus 13. So equation of plane is basically 4x plus 20y minus 21z is equals to plus minus 13. So this is basically the equation of plane which is touching the surface of this ellipsoid. So the question further says that determine the coordinates of point of contact. Okay, so let x naught, y naught, z naught be point of contact of 2, and let's name this equation of ellipsoid as 1, of 2 and 1. So if that's the case, then x naught, y naught, z naught must be lying on both plane and the equation of ellipsoid. So tangent at 1, tangent to 1 at point at any arbitrary point x naught, y naught, z naught will be basically 4x naught x minus 5y naught y plus 7z naught z is equals to minus 13. So if I simplify it, let's name it as 3. So if this is basically the touching point of 1 and 2, then tangent plane at basically x naught, y naught, z naught is this. Then the plane 2 and plane 3 must be representing the same plane, and if that's the case, their direction cosines of normal must be proportional. So using that, I will get 4x naught divided by 4 must be equals to minus 5y naught divided by 20, that must be equals to 7z naught divided by minus 21 is equals to minus 13 by plus minus 13. So from here I got x naught is equals to minus y naught by 4 equals to z naught by minus 3 is equals to plus minus 1. So from here I got my x naught as plus minus 1, y naught as minus plus 4 and z naught as minus plus 3. So the point of contact are basically 1, minus 4, minus 3 and minus 1, 4, 3. So these are basically the point of contact with respect to these two given planes. Also you can just substitute these value in equation of plane and the ellipsoid equation to basically verify that this is a touching point of the equation of plane and the ellipsoid. So that's all. There is one more question related to diametrical conjugate diametral plane, but I didn't read that topic. I'm not basically clear with the concepts of that topic, so I'm not solving that question in the video. So you can solve that by yourself, or you can look up for solution somewhere else. Thank you for watching.